Start recording. Okay, so we left off last week. We were talking about real solutions, or on Wednesday, not last week. Real solutions, short range ordering. Sweets, I'm trying to teach. So, sorry, my daughter. Say hi to everybody.
Hi.
Stick your head in. Okay, so we were talking about real solutions and deviation from ideal and regular, and we talked a little bit about short range order, that if there's a preference for dissimilar type bonding, we have a more ionic character and we'll tend towards ordering in the solution. And if it's there's a preference for like type bonds, we'll have a clustering and perhaps a miscibility gap that forms. And if there's a big size differential, that leads to elastic strain or perhaps even interstitial type solutions, depending on how different the size is. So we talked a little bit about short range ordering and glasses and metallic glasses. And we left off with long range ordering, where there is a clear energy preference towards forming these ordered structures so that we maximize certain types of maximize the bonding in certain ratios, right? And we take a big entropy hit when forming long range ordering, because obviously now we have far fewer configurations. But if the energetics work out, the enthalpy term works out, that it's very favorable to form these types of bonds, then the structure will reduce the number of possible configurations at the balance for a lower internal energy and enthalpy. And we finished talking. We finished up with talking about nickel superalloys, and these superalloys are responsible for the advances in jet travel, and the structure of them is really cool. These are composites of gamma phase, which is a random solid solution of nickel and aluminum for the most part. There's actual superalloys have 7-8 components to them, but the primary is nickel and aluminum. And the gamma prime phase, which is an ordered structure, right, which is right here, this little region on the phase diagram. And this is nickel 3 aluminum, and most of the time we want to be in this 2-phase region here. So we have a mix of gamma FCC structure and the gamma prime superlattice, right? And we left off by saying that this, even though it looks FCC still, this is no longer an FCC unit cell, right? Because we don't have the translation symmetry from the nickel site to the aluminum site. The crystal structure is actually simple cubic, but instead of just one atom at each lattice site, we now have 1 aluminum plus 3 nickels, right? And we can now translate, do our endless repetition of stacking up these cubes. Okay, so this is what the microstructure looks like for these high density gamma prime structures. These cuboidal-like precipitates here are actually the gamma prime, and these little channels in between are the gamma, right? So quick question here, why are these cubes? Any idea? This feeds into
Audio kind of cut out. Why are they what?
why are the precipitates cuboidal?
Are those individual cells or like a collection of them?
These are individual precipitates. So each one of these cubes is gamma prime, and then these channels in between are gamma, or FCC. And this is our superlattice ordered phase.
I'm going to take a guess here.
Okay.
I'm guessing that they're cubes because since this is a solid precipitate, they have a very ordered structure, and having them as squares follows the natural shape of the lattice. They're only separated by the grain boundaries in between.
Yeah, so sort of. You're sort of on the right track here. So the reason is anisotropy and interfacial energy, right? So there's a big difference. The 001 type planes, right, which are the sides of the cube, have a much lower interfacial energy than some other planes, right? They match up better, right? If I stack this face against this, the top face of the gamma against the bottom face of the gamma prime, there's much less distortion than if I did some other interface, right? And so having the cuboidal shape allows me to have a coherent interface all the way around, or semi-coherent interface, and it reduces the energy. So why are these things, and this is stuff we'll talk about later on in the semester, but why are they called superalloys, right? And it has nothing to do with the fact that the gamma prime is a superlattice structure. It really has to do with the properties. And it has something to do with this, with if this is yield stress as a function of temperature for some current generation superalloys. So if you get on an airplane today, these CMSX type alloys are what's in the GE engines. So these are the properties of actual current generation alloys. How does yield strength and temperature usually look? Right? It's usually monotonically decreasing. The higher you get, the weaker your material gets. Superalloys have this anomalous yield point behavior, where there's a range where they actually get stronger as you increase the temperature, right? Then of course it falls, right? It has to fall eventually, but this behavior here is what makes superalloys so super. And the reason why this happens is actually really complicated. It has to do with the way partial dislocations can move through the gamma prime structure, and it's a whole really interesting 45-minute lecture in the advanced physical metallurgy class. So we're gonna skip it for here, but it's a really cool property of these materials. Okay, so to wrap this up, I want to talk about another old dead white guy, William Hume Rothe. He was a very famous metallurgist and material scientist. He founded the Department of Metallurgy at Oxford in the 1950s. He had a lot of scientific contributions. I think one of my favorite was he was the founding editor of the Journal of the Less Common Metals, which basically at the time meant anything but steel or aluminum. The interesting thing is he lost his hearing as a graduate student because of an infection. He got sick and ended up going completely deaf. But at the time, you know, in the early 1900s, a handicap like that would have been sort of the end of the career for most people. You know, the society was not nearly as inclusive to people with any kind of differences back then. But he persevered, managed to finish his PhD, and went on to a really successful career. He was a really famous scientist, kind of, you know, the leader in the field. And there was he organized a big conference, very famous conference on metallurgy in the 1950s at Oxford. And because he was deaf, he essentially would have graduate students sit next to him and transcribe the talks as the speakers were going, and write them all down so that he could participate in the conference. And one of these graduate students was a mentor of mine, a British metallurgist by the name of Rothe, who did a lot of very fundamental work on recrystallization and recovery. But anyway, so Roger was sitting next to William Hume Rothe at this conference, and a speaker came up, and of course, being deaf, Professor Hume Rothe didn't have great volume control, and he whispered to, or he thought he whispered to Roger, "Don't write this down. This talk won't be worth reading." But of course, he shouted it, so the whole hall heard it right as this poor speaker was getting up, and it sort of, you know, obviously took the wind out of his sails that the most famous person in the room basically just said out loud that your work is shit. So that's the funny story about Hume Rothe. Okay, so why am I pointing this out? This is stuff that wasn't in the reading, but it really should have been, I think. And what William Hume Rothe did was come up with a set of really basic rules that describe when you're going to be able to form a solid solution in a metal, or when you're going to form, have a miscibility gap, or form an intermetallic or an ionic compound, right? And these rules, while sort of focused for metals, are also hold true for a lot of other type of solutions. And I wanted to make sure you guys at least saw this, because this is one of my material science rules of thumb, right? I have this sort of basic toolkit in my brain that whenever I'm faced with a new problem in material science, they're like they're what I use for getting a first order approximation, right? And so some of those are these Hume Rothe rules, right? Anything that has to do with dislocations, right? My go-to is, anyone know what's the energy of a dislocation? Right? GB squared, right? The shear modulus of the material times the Berger's vector squared, right? So anything to do with dislocations, GB squared. The strength of a material is going to be proportional, for a crystalline material, is going to be roughly proportional to the square root of the dislocation density, right? Unless there's other things in there. Right, for any material that has significant ductility. Anything to do with diffusion, right? Square root dt, right? So these really sort of basic things of ways of thinking about the world get me through 90% of material science problems, at least to a first degree approximation, right? And so I'll be pointing these types of things out throughout the class as to where my, what I think are really sort of important but simple ideas. And these Hume-Rothe rules are one of those. So what are they? Basically, it says the atoms should be about the same size. The solute and the solvent, if they're going to form a complete solution, have complete miscibility in each other, they shouldn't really differ by more than 15% in the size, right? And why that 15%? Well, that's about when they begin to deviate by more than that, the elastic interaction, the bond stretch becomes too much, right? And those A-B bonds have way too much of an energy penalty, right? So you'll start to get really significant clustering, and you'll get a miscibility gap, right? The crystal structure of the solute and the solvent should be similar, right? We're more likely to get a solid solution between two FCC metals than you are between an FCC and a BCC, right? When they have similar valency, right? When the electronic structure is similar, you're less likely to have covalent bonds that form, right? If you're going to have, if there is going to be a difference, you're in valency, you have a dissimilarity, right? That the metal with the higher valence is likely to dissolve in the metal with the lower valency. So that means something with the valence of plus X is going to have more solubility in a metal with +1 than the other way around, right? You'll be able to put more into solution before it falls out. And the solute and solvent should have similar electronegativity, right? If the electronegativity difference is too great, they're going to form intermetallic ionic compounds instead of solid solutions, right? So 4 pretty simple back of the envelope rules, but these are really powerful for predicting phase diagrams, right? Okay, so we know what's coming up next because I've got it right here. Okay, so I don't want to put too much of a stress on it, but this is probably the most important topic in the whole semester, right? And it's also a review because you did see this from Professor Akbar. But this is like so central to everything that we're going to be talking about. This notion of this common tangent construction for equilibrium in heterogeneous materials, right? Time for your nap. Am I boring you that much? Okay, so how do we motivate this notion of equilibrium, right? And this is an area where the reading really overcomplicated the discussion, okay? So we know how to handle a single phase, right? We know what the Gibbs free energy of mixing looks like. We know if we're going to have solubility or phase separation. But how do we extend to stability and equilibrium when we have 2 competing phases, right? So in this case, we have...
Is that rhetorical?
What's that?
Was that a rhetorical question?
It's a rhetorical question, yeah. Right? So in this case, we have 2 elements, A and B, that we're mixing together, two components to our mixture, and they each have different crystal structures, alpha and beta, right? So we can draw the free energy curves for alpha and for beta, right? And we can see that at pure A, alpha is clearly favored over beta, and for pure B, beta is clearly favored over the alpha structure. And if we're in the dilute regime, it's no problem, right? If I don't have a lot of B in here, alpha is clearly so favored over beta in free energy, right? That everything is just going to be happy as being alpha. Same thing over here. If I have dilute A, everything's going to be happy being beta. But what happens when I have a solution that's in the middle here, and alpha and beta have similar free energy curves, right? How do we guarantee that we're in the minimum free energy configuration, right? Because obviously, if I just have a mixture of alpha at this concentration, and a mixture of beta here, right? If this is my overall composition, right? If I take these two free energies at equal portions, I know that I'm not going to be at the minimum, right? If we come here, right? If I have x naught or xa times g alpha here and xb times g beta here, and I add them together by the, weight them together by their fraction, I'm not guaranteed to be at the minimum free energy. In fact, I can tell you that I guarantee you that you're not going to be at the minimum free energy. How do we get there? We can actually lower our free energy by having alpha be at this composition and beta be at this composition, right? How do we actually get to equilibrium, right? And this is where the beauty of chemical potential comes in, right? What does chemical potential tell us? How happy a given element is in a phase, right? And we're going to have material transport. The chemical potential is our driving force for material transport or mass transport, right? So if we're at equilibrium, let's take a look at this picture where we've just started to separate. If I'm at alpha of this composition, what's my chemical potential of B? Right? I draw my tangent over to here. So my chemical potential for B is way up here. And what about in beta? Right? If I draw my tangent here, my chemical potential for A and alpha is B and alpha is up here, and my chemical potential for B and beta is way down here. What's my system going to do? I've got a chemical potential gradient now for B. I'm going to move from my region of high chemical potential to my region of low chemical potential. So my B is going to leave alpha and go to beta. And when does it stop? Right? When that's not a rhetorical question. Someone throw it out there. When does it stop?
Equilibrium.
At equilibrium. But what does equilibrium mean in terms of the chemical potential?
The potential of U B beta is equal to U alpha.
Right? The mu B beta and mu B alpha, the chemical potential of B and beta has to be equal to the chemical potential of B and alpha, right? Then I have no driving force for material transfer or mass transfer from A to B, from alpha to beta, right? So when does that happen, right? If my chemical potential is given by this tangent line, so when I have a line that's tangent to both free energy curves, right? So that's going to tell me everything I need to know. So if I start here at composition X naught, I'm going to phase separate to alpha of this composition and beta of this composition. And when I do that, the chemical potential of alpha is the same in both, the chemical potential of A is the same in both alpha and beta, and the chemical potential of B is the same in both alpha and beta, and I have no more driving force for mass transfer. Right? So I really can't stress, it's a really simple idea, right? We want to find where the chemical potential, the definition of equilibrium is going to be where the chemical potentials of all the species are the same in all the phases. Right? Or the chemical potential for each species is the same in all the phases, because the chemical potential of A doesn't have to equal the chemical potential of B. Right? I want to be clear. I said that a little too quickly. And saying of instead of for. But it's generally a really basic idea that a lot of people just miss, right? And I know Professor Akbar covers it, but he covers a lot of really important stuff. So you probably it never seems to connect until you see this 3 or 4 times, right, through your life. And then it's like this really basic thing. But until then, keep refreshing yourself on this. So question.
I have a question about the figure on the right.
Okay.
So I understand that the tangent slopes connecting the two curves at the bottom are at the equilibrium point.
Yeah.
What is the point center where the two G curves intersect, if that's not equilibrium?
This here?
Mm-hmm.
This point here, that's definitely not equilibrium.
I am aware of that because
so
the G is not minimized.
Yeah, so that just tells you where the free energy of the individual curves is equal to each other, right? And it really has no significance overall, right?
Okay, just wanted to clarify.
Yeah, right. So what you have is the free energy of your solution after your heterogeneous material, right, is going to be given by this point here, GE, right? So the driving force for the phase formation, right? If I start with pure alpha and I mix in this much B, so I'm at this composition here, the driving force for the formation of beta is essentially going to be this difference in free energy here.
Also, should the one on the left be G alpha equilibrium, not G beta?
The one on the left here?
No, the one on the right figure, left equilibrium point.
So
the one
this
above
point, yeah, so this point, oh, here, yes. I didn't realize that. There's a typo in the book. Damn it. There's lots of typos in the book. This should be G alpha. Right here. Dang it. Thank you. This is what I get for cutting and pasting out of there. Okay, so, right, think about this curve. Spend lots of time, meditate on this curve. Be one with the common tangent construction, right? If you internalize the significance, right, the meaning of equilibrium is when your chemical potentials are equal and you're not going to have any driving force for mass transfer, right? Everything about this makes sense. If you don't think about it in those terms, this is just sort of like an arbitrary thing that doesn't really matter much, but it's really, really important. Okay, so if we look here, this figure is not as important, right? So, but there's a thing I want to point out that's may help you understand. So if we start from pure A and we add A, and we add B. So we start with pure A, we add B, we move down these free energy curves, and our tangent at pure A obviously meets right here. As we move down, our tangent, the intersection of our tangent with our axis moves down, and this distance here is RT, natural log of our activity, right? So until we get to the common tangent, our activity of A drops, right? But then when we're at the common tangent, our activity plateaus, right? Because once we're in this composition range, right, we're dictated by our common tangent construction, and our chemical potential, while we have these two phases in equilibrium, always stays the same. And it's not until we reach this point, and now we're fully beta, that our activity begins to change because our tangents are moving, or our chemical potential changes, right? We could make this same plot instead of activity with chemical potential, and it would look basically exactly the same, right? But what's important to know is that while we're in the two-phase equilibrium region, our chemical potential is constant. It doesn't change with composition. What does change is the composition of our two phases to keep our chemical potential even, right? Okay.
So why does that eventually fail?
Eventually fails once you reach 100% of alpha and 100% of beta, right? It's just only in the two-phase region. Right? Okay, so now, the common tangent construction gives us the composition of the two phases, but what about the relative amounts, right? And for that, we have to use a lever rule, right? So the amount of A we have is the ratio of this line length over the whole line length. And the volume fraction of B is equal to the ratio of this line length over the whole thing. So it's really an inverse level rule, right? So the fraction of A is the length from X naught to beta equilibrium point, and the fraction of B is the ratio of alpha naught to X naught over the whole line. So it's really an inverse rule, but it makes sense, right? As we're out here, right? If my composition is close to my alpha equilibrium, right? I don't need to move a lot of B into beta to be able to move back here, right? So if I'm close here, I'm going to be primarily alpha with just a little bit of beta. If I'm over here, I'm going to be mostly beta with just a little bit of alpha, right? So you can, of course, use that to remember where you're, which side you need to take for which element, right? But this is the same lever rule that you learned on your phase diagrams in 2010. It's just in the Gibbs free energy space directly rather than in the phase diagram. Okay. So what about phase diagrams? Well, a phase diagram is nothing but a collection of these free energy curves for a given temperature. All we're doing is plotting the tie lines on our phase diagram are nothing but these common tangent points on our Gibbs free energy drawings, right? So if we take a really simple phase diagram, this is a phase where this is a system where A and B are completely miscible. They make a complete, they have a solid, complete solubility in both the liquid phase and in the solid phase, right? At high temperatures, obviously the liquid is the lower free energy curve everywhere. As we move up, the liquid and solidus curves for Gibbs free energy curves intersect, and we have a region where solid and liquid are in equilibrium. And these tie lines on the phase diagrams are our common tangent points. We just drop them straight down, right? And by translating these curves through various temperatures and plotting the tie lines on the temperature composition graph, we get a phase diagram, right? So this common tangent construction is how we arrive at all of our phase diagrams, right? So it's really easy to do for a simple one, right? And then of course we can apply the lever rule here as well, right? Because if these points are just the same as our common tangents, right? We can apply, and we have a lever rule in this space. Obviously, we have a lever rule on this line, right? So we can, you know, if we're at a composition here, right, we can do exactly the same calculation, right? So some places call it the first lever rule and the second lever rule. It's actually the only lever rule, right? Because you're talking about distances of between these common tangents. Okay, so what about systems with a miscibility gap, right? That's the next level of complexity on the phase diagram. Okay, at high temperatures, no problem, right? Our liquid is everywhere lower than our solid, so we're completely liquid. We come to this intermediate temperature range where the solid drops below the liquid. So we have a common tangent over here and a common tangent over here that we can use to define the regions where the solid and the liquid are in equilibrium with each other. We have a region on the A-rich side and we have a region on the B-rich side. But here we have if we keep dropping the temperature down, we have a region where in this case, our delta H of mixing is high, right? So we have a hump in our Gibbs free energy, right? But again, it's still given by this common tangent construction. So what we have here is the case where A and B both have the same crystal structure, right? Say FCC, for the sake of argument. But in this region in between, we have a mixture of FCC at this composition and FCC at this composition. So they're two different phases because they have different compositions. But once you get high enough in temperature, and we lose this hump because the entropy term dominates instead of the enthalpy term, so we now have a curve that looks like this, we just have one phase, right? We have complete solubility here, right? So these Gibbs free energy curves tell you everything you need to know, right? We can look at a system with a eutectic, In this case, now we have A and B in their pure form have different crystal structures, alpha and beta. So we have a region of our phase diagram where liquid is in equilibrium with alpha, liquid is in equilibrium with beta, and then we have one special magic point where we have a common tangent between alpha, liquid, and beta. And that's called the eutectic point, right? So here at the eutectic point, we have three phases in equilibrium: alpha, beta, solid, the alpha, beta, solid, and the liquid. So if we are exactly at the eutectic composition and we cool down, we're going to be liquid, 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 and then we drop the temperature just a tiny bit more, and we're going to freeze out into alpha at this composition and beta at this composition, right? Right? So we go from having three phases in equilibrium, we drop the temperature down just a little bit, and now we have two phases in equilibrium, right? Because we no longer have a common tangent, right? You can't draw a straight line anymore, right? Whereas if we go up in temperature just a little bit at this composition, the liquid is clearly the lowest phase, right? So the you'll see if you take the physical metallurgy next year, you'll spend time talking about the essentially the curvature of this Gibbs free energy and how it relates to the curvature of the solubility line on the phase diagram, right? And how that relates to design of metallic systems. If you want a system with good that has lots of precipitates that come out, you want something with a high degree of curvature of this solvus line here. And that's going to be tied back to the Gibbs free energy of your partial molar Gibbs free energy curves, right? So there's a ton of information that we get from these things, okay? The more complicated, complex the phase diagram, it's all the same process. You just plot the Gibbs free energy, the partial molar Gibbs free energy curves for each of the different phases and connect them all up with your tangents. And that tells you where all the tie lines need to be, right? So it's a simple process, but it's tedious, right? Especially if you look at phase diagrams that have tons of phases like this one here, right? Calculating the free energy curves or measuring the free energy curves for all the various phases can be a royal pain. So there's something deep here that a lot of people miss at first. Because the stability has to do with this common tangent, right? What this says is that the composition of our phase is not just dependent on the free energy curve, the free energy of the phase itself, but also the free energies of the phases near it on the energy diagram, right? It also means that if I'm drawing these tangent curves, that the composition may differ than what we would expect stoichiometrically from the crystal structure, right? An example of this is copper, the aluminum copper system, right? This was what was brought out in your book, that the from the crystal structure, we would expect Al2 copper, aluminum 2 copper, but the way the free energy curves hit, we barely kiss that point. So most of the time, the precipitate that forms has a composition that is less than what we expect stoichiometrically. Right? Now, what happens if we consider this curve here, and we have 3 phases, alpha, beta, and gamma? What happens as this parabolic or approximate parabola that defines B? What happens is this gets narrower. So instead of this wide curve, we have a really, really narrow one. What happens to the tangent then?
Does it become more linear?
It becomes more, we have we end up with a narrower composition range, right? And so as this becomes more steeply curved, we end up with the 2-phase region narrows and eventually becomes a line compound, right? So when you have something that has a highly ionic character, like these intermetallic compounds, right? If I have a ionic compound, I need to maintain charge neutrality, right? And so if I change my composition, now I violate charge neutrality, and I have a huge energy penalty for that. So the system really doesn't want to be at any composition other than the stoichiometric composition. So the more ionic the bonds, the narrower this 2-phase region is on the phase diagram. And that has to do completely with the shape of these free energy curves, right? So the higher, right, the deeper these parabolas, the lower the composition, the span of the composition that you're going to get, right? Okay, and so we finish there. We'll finish up Monday with the Gibbs phase rule, and then I want to look at the aluminum copper phase diagram in a little bit of detail to give you an illustrated example of multiple phases. And then we'll talk about the thermodynamics at interfaces and the Gibbs-Thomson rule before we look at the reading that we had on polymer solutions, right? And dealing with solutions other than metals and simple molecules. What happens when we have really long, complicated molecules? Okay, have a good weekend, everybody. And look for the mastery questions to come up sometime this weekend, okay? And there's no due date for those.
Quick question.
Yeah.
When is our first exam again?
The schedule, it's on the class calendar, or it's on the syllabus. Hold on. Let me look at the date. Wednesday, October 21st is the midterm. Right? So still a bit of time. Right? And the reading will be due Wednesday because the reading quiz, I didn't get published to Carmen. So I'm going to give everyone some extra time on the reading. Okay. Have a good weekend, everybody. We will catch you later. Stop recording.